You'll have heard a lot of stuff in the newspapers over the last few months about how elite universities don't select students from different kinds of backgrounds. So I want to tell you now that I grew up on a North London council estate, and I'm head of the chemistry department at Imperial College. Not only is having that kind of background not a block to being a student here, it's clearly not a block to being a professor here. And so regardless of your background, do please apply to Imperial College if the thing that excites you in life is science. That's the only thing that we're interested in. And that you're good at it. Okay, so chemistry for a cleaner world. What's this all about? Right, this is how I start the morning, waking up to this thing, which is my alarm clock. And when you look at it, you might see an alarm clock. What I see are a variety of products of the chemical industry. And so you can see there are plastics. There's plastics at the transparent front of the clock. There are plastics holding the alarm clock together. There are plastics inside the clock. Liquid crystals. Liquid crystals haven't been around that long, more than many of you have been alive, but not that long. These are also products of the chemical industry, and everyone that's got a mobile phone on them, which I'm sure is all of you, will have a liquid crystal display there. We'll come back to that later. And inside the clock, there are electronics, there are silicon chips, there are junction, there are welds, there are seals, and all of these only exist because of the chemical industry. So now as my day continues, I finally drag myself out of bed, and the next thing I do is clean my teeth. And what you might see here as just toothpaste in a tube, I see as products of the chemical industry. So the tube that the toothpaste is held in, plastics again. The toothbrush, plastics again. The toothpaste itself, 18 different ingredients from the chemical industry making that toothpaste. So you get the game we're playing. Next, I shower. What can you see? Ooh, come on. Shampoo. Okay. Yeah, shampoo. That is a product of the chemical industry. What else? Soap. Soap is one of the oldest products of the chemical industry. What else? How about more plastics? There are plastics in the bottles. There's plastics of the perhaps you can't really see it. There are plastics of the shower screen. In fact, all of my shower is made up of plastic. Shower gel, 20 ingredients. Shampoo, 31 ingredients. So, okay, hands up, who thinks most of the ingredients in the shampoo are to clean your hair? Very smart. I wouldn't have asked the question if that was the answer, would I? Most of the products in the shampoo are to make it feel nice. And so, in order to make it run out of the packet without running out completely or getting stuck inside, just making it the right viscosity to be able to flow out nicely. Ingredients to make it feel nice and creamy in your hand before you use it. Ingredients to make it feel nice when it's on your hair, to make it foam just enough that you think it's doing a good job, but not so much that then there's foam all around your feet. 31 different ingredients of the chemical industry. Right, then I have breakfast. Try again. What can you see here? Oh, hang on, one at a time now. The cereal, you're right, the food. Food additives, preservatives. Not in this cereal, sometimes colouring. In this cereal, added vitamins. And yes, you? Plastic again. Plastic for the milk bottle. Plastic inside the packet for the cereal. What else? Wood. Well, cardboard. And finally? Oh, wood, the table. Actually, my table's plastic. But it could be wood. It could be wood. How about dyes? The box is covered in inks and dyes, hundreds of different colours, literally on the one box, all products of the chemical industry. Oh, and I forgot, the bowl, ceramics. Ceramics are made by chemical processes. This is me, walking to work. So what can you see here? The phone. Yeah, the mobile phone, we'll see, is absolutely stuffed with products of the chemical industry. What else can you see? A ring, actually, yeah. Several different metals. Platinum, white gold, 2 types of yellow gold, and rose gold, in fact. Well spotted. What else can you see? Dyes in the clothes. What about the clothes themselves? Fabrics. That's a nylon jacket. And so these are all products of the chemical industry. But what haven't you noticed? The wall, the bricks, the cement, they're all made by the chemical industry. So in your mobile phone, it's got a plastic case. Again, it's got all of those electronics that I had inside my alarm clock. It's got a battery and more liquid crystals, all products of the chemical industry. I'm glad no one said dye for the hair. It's real. Okay, and then I get on a bus. What do you see now? The bus, okay. So the bus is made out of mostly metal, rubber, more plastics, metal, paints. It's all painted red, isn't it? So again, a mass. Someone did say glass, didn't they? And the road. The road is asphalt. Well done. The road is a product of the chemical industry as well. I left that one off because I didn't think anyone would spot it. There you go. So a mass of chemicals takes me from my home to the tube station. And finally, I get on the tube. So what can you see here? The newspaper. Yeah, the paper itself. The ink. Paper. What was being said over here? Plastics again. Metal. Pole. Fantastic. There's loads of stuff here. So there we go. Plastics, metals, dyes, fabrics, inks, paper, all products of the chemical industry. I'll tell you what, that's something that... Can anybody tell me what tube line this is? Bakerloo. Well done. How do you know it's the Bakerloo? Brown poles. It's one of the things that's so fantastic about plastic. So the plastic that these poles are covered in is completely colourless, which makes it really, really flexible. So what people can do is they can just mix in the appropriate dyes to get any colour they want. And well done those of you that have spotted, on your underground trains, the vast majority of them, what you have is different coloured poles that match the colour of the line. And that's because our dyes made by the chemical industry and our plastics made by the chemical industry are flexible enough to allow us to do that. There is one line where it doesn't happen on, which is the northern line. And the poles are yellow, and there's a little black band about halfway up them. And what's that black band made out of? Plastic. So really, really important in letting us have the kinds of things that we want today. So, do you know what this is? Fantastic. Roughly how many elements? 100 and a bit will do. A lot of argument about that. A lot of fuss about it. Okay, so how many elements do you reckon that I came across this morning on my way into work? 5? Hands up for 5. More or less? 10? Bit more? 15? More? 20? 25? Or maybe a bit more? 30? 35? 40? 45? 47 elements I came across on my way into work this morning. And you can see from all over the periodic table. So metals down this end, lithium in batteries, sodium in the salt on in my cereal. Going through here, these transition metals, you know the transition metals. So they're used in electronics. Lots and lots of different applications in electronics come from those transition metals, all those funny little welds and joints that allow silicon chips to work. Main groups, solid state materials. They turn up again and again. In lots of those plastics, they're incorporated to give them the colours or the properties that we want. But nearly half the periodic table. And in fact, if you took out the elements that are radioactive and so that we can't use them, you have about 2/3 of the available elements I used in my journey to work this morning. So what I want to say to you is chemistry is really, really important. The chemical industry is really, really important. Which of the things that I showed you this morning, with the possible exception of the alarm clock, would you like to not see, to not have, to not be able to use? Probably none of them. Okay. And what kinds of materials have we seen again and again and again? Plastics. So we're going to now do a little bit of some demonstrations about plastics. And so the first thing I need to do is borrow you, Maggie, and my two assistants, Mel and Laura. They're going to do all the difficult stuff. I'm just going to do the talking. So this is what we want you to do. So you're going to start off holding the hands of the person next to you. Okay? And when we say go, it's all right, wait until after we've done it. When we say go, you let go and hold the person on the other side of you. So go. And so you'll do this. Okay? So that's what we want you to do. So all get ready, hold your hands. Thanks, Maggie. I think go and join a row then and do it. Are you all ready? You're all holding both hands? Okay, so go. Right. Now, can you stand up for me? Keep holding hands. Lovely. So put your hands up. Fantastic. So you have become polymers. And polymers are what plastics are made out of. They're long chain molecules with lots and lots of repeating units. Normally, absolutely the same units. You'd be a heteropolymer because you're not all identical to each other. So anyway, so you are all polymers. And you see how you formed these chains, some long chains, some short chains. Well, that's what a real polymer structure is like. It's got some long chains and some short chains and some very long chains and some middle length chains. Okay, fantastic. Sit down. So now you know what a polymer is. We now need to find out why a polymer might be important. So I need 2 volunteers from the audience, please. Yes, okay, you and you. Why not? So, yeah, one of you is going to come and work with Mel, and one of you is going to come work with Laura. But before you do, what's your name?
Risha.
Risha. So, this side of the room, when we get going, you're going to support Risha. So I want you all to shout her name. Risha. Fantastic. And your name is?
Immaculata.
Immaculata. Wow, that's going to be a mouthful for you. So you lot are supporting Immaculata. Get ready? Fantastic. And so what Risha and Immaculata are now going to do is they're going to make a polymer. Right. And so what they'll be doing is they've got, you can see we've got bottle A and bottle B. And we're going to mix bottle A and bottle B. Those are monomers. Those are the things that the polymer is going to be made up from. And then once they've mixed them a bit, they're going to have to stir them and stir them and stir them to make the polymer. Okay? So another quick practice. This side. Risha. This side? Right. Try it again. This side? Fantastic. Okay. You'll see they're putting glasses on. They're putting lab coats on. That's just because we've got to be a bit careful in case they spill the stuff over them. And we always do chemistry as carefully as possible. And we've got gloves for them as well. The stuff they're using isn't particularly hazardous. It's just we always take care when we do chemistry. Oh, nearly got them on. Right, are you ready to go? All right, oh, another glove. Or maybe try a completely new one. Sometimes they get a bit sticky. Oh, hang on. No, there we go. We're there. Right. So, you might as well be on the side for the room you're in. So, Risha over this side, Immaculata over there. Are you ready? Okay. Go. Louder. Keep going. Right. Now, let's have a look. Is it starting? Oh, yeah. It's getting going now. I beg your pardon. Oh, here they start. Ooh. Yeah, we're getting some bubbling in here. You'll see it in a minute. Ooh. Are we hot? Yeah, they're reacting. So do you know why I did that? Why I said, are they hot? Yeah. If you get an exothermic reaction, if you get some heat given out, then we know the reaction's starting. Oh, but it's taking its time, isn't it? Oh, are we going to need to go again? No. We're going to have to wait a minute. Dum-be-dum-dum-dum. Ah! And here it comes. Oh, well done, Risha. So now what we've got happening here, it's taken, what we've got happening here is it's taken a bit of time for the reaction to initiate, get going, and now we're making polymer. And you can see that the form of the polymer is coming from gas bubbles being given off. It's actually water that's being given off, but it's nice and hot, so it's coming off as steam. So, thank you very much, Risha. Thank you very much, Immaculata. Let's give them a round of applause. So the polymers that they've made here, that I now aren't stopping. Oh, well, they can always change the carpet. The polymers that they're making here are polyurethane. Some of you will have heard about polyurethane. So who's this? Why on earth would I be showing a picture of Usain Bolt now? Trainers. Fantastic. And actually, the person that talked about the road, the track. Both the track on which he won his gold medal at the World Athletics Championships and broke 2 world records in the 100 and the 200 meters in Berlin. The track is made with polyurethane. Fortunately here, he's absolutely pointing at it. He's pointing at the polyurethane in his trainers. And it is only with the help of polymers like polyurethane that he can achieve the amazing results that he achieved. And so polyurethane really is an important part of being the fastest person in the world. So, where do you think this photograph was taken? Maybe in a reservoir? A lake, maybe? In the Thames? Did somebody think it was in the Thames? Yeah, it's on water somewhere, isn't it? Does that help? The world, yeah. It's out in the sea somewhere, isn't it? This is where it was taken, in the middle of the Pacific Ocean, as far away from habitation as it is possible to get. And we saw that rubbish. Let me take you back. So at the furthest point from habitation that we could find, what do we see here? Plastics. We also see dyes. There's a football there somewhere. There's a football there. And unfortunately, what are these? These are products of the chemical industry. These are products that we use every day. Half of those pictures that I showed you as we started the lecture had these products in. So suddenly it's not all so rosy, is it? So is there anything that we can do about that? No, this is just more chemical products. This is a thing called a landfill site. So when you don't throw them into the sea, and you dispose of them properly, this is where your rubbish, most of your rubbish that you don't recycle, ends up, in landfill sites. Unfortunately, here in the United Kingdom, we've run out of holes of ground in the ground in which to put rubbish. Literally, there is no more space to put it anywhere. And so we need to find something to do about our rubbish. The first thing that we can do, that you can do, is to think about reuse. And this is reuse, so there's a water bottle. You empty it, you drink it, you go buy your water bottle and you drink it. And you have a choice. You can throw that water bottle away, or you can fill it up from the tap and use it again. And if everybody used their water bottles twice, there would be half the number of water bottles to throw away. If everybody used them 10 times, there'd be a tenth of the number of water bottles to throw away. So that's something that we can do. And we should all do. We should all think about reusing things until we no longer can. Lots of people don't like bottled water. Lots of people don't like tap water. But bottled water is actually worse for you, health-wise, than tap water is. The bacterial load, the amount of bad things, that's allowed in a bottle of water is 10 times what Thames water would be allowed to run out of your tap. So actually, there's another good reason to reuse your water bottle. The other thing that we can do, and we all do this now, I hope, you probably do this at home, is recycle. So recycling is different to reusing. Reusing is taking the product and using it again for the thing that it was made for. And that's absolutely the best thing that you can do in terms of reducing the amount of waste that you generate. Recycling is the next thing down on the list of things that you can do. And so when you recycle something, you take it in the form that it was originally made, and then you make it into something else. And so here we have literally a plastic bag that used to be a plastic bottle. And you can buy fleeces that are made from plastic bottles. There are all sorts of things that you can do. Recycling is an important thing that you can do. Right. Because when we make things, we make a lot of waste. So this is a toothbrush. You're familiar with the toothbrush? This is a 1 kilogram weight. Just come round here. If you start picking it up and passing it along, so there you go, toothbrush, 1 kilogram weight. Feel the difference between the two. every time a toothbrush is made, over a kilogram of waste is generated. Does that sound sensible to you? That's pretty mad, isn't it? Okay, so what can chemists do to help this? I think you now have green chemistries in some of the school syllabus, yeah? Yeah. Have you done it yet, or is it coming along later? It's coming along. So what I'm going to talk to you now for a little bit, for about 10, 15 more minutes, is green chemistry and what green chemistry can do. And unless, you think that green chemistry is a small activity, I think I just put all of these. So these are scientific journals. Green chemistry, I'm on the editorial board for that. Chem Sus Chem, the rivals, I'm not on the editorial board for that. Green chemistry letters, we don't like them. And some books on green chemistry. It is a major, major, major activity. It is no longer a new and rare area of work, which is why you're getting it in the A-level syllabus. So what does green chemistry do? The long and short of it is, green chemistry is trying to provide for us all of those products that I talked about at the beginning of the lecture, without leading to a kilogram's waste for every toothbrush that we made. So how can chemists deal with that? What's our part to play? Well, this is to remind me to talk about dematerialisation. So maybe not beam me up, Scotty. But what we can try and do is use less stuff. And the first thing that green chemists do is this thing called dematerialisation. Does that sound ever so special? It's not really. Because that's it. I couldn't do this without advertising. I searched the internet for this picture without advertising. So you're all familiar with dematerialisation, and so that's when you use concentrate instead of using the old-fashioned version. So when I came to university, I used to get sent to university by my mum with a Red Cross parcel, and the packet of soap powder was easily, the depth of this, standing this high and this big. I could carry it just about. It was huge. And I got about as many washes out of it as I would now with a 1.5 litre liquid bottle. So a lot less stuff being used. Less stuff is less waste. Less stuff is less transport costs. Less stuff is less packaging. All of those different things that feed into making that kilogram can be reduced just by having less stuff. So that's one thing. Right. So now we're going to move on to our next demonstration, and let's see how many. So what I need now are 5 boys and 5 girls, really. So, the girls' hands go up really quick. 1, 2, I've already had you, haven't I? 1, 2, 3, 4, 5. Okay. So if you come down, okay. And 5 boys. 1, 2, 3, 4. Go on, 5. Go on, we're not going to do anything nasty to you. And so what we're going to do now is demonstrate a reaction to you. And so if you think about you want to make something, so you're going to make some chemical, and then the easiest way to make something really is just to take 2 things that you're making it from and add A to B. And that's called an addition reaction. And that's what we're about to do now, as soon as they're ready to go. Thumbs up? Oh, we're short a girl. Can I have another girl? Go on. But I've got 6 boys now, I think. I've got an extra boy. That's what happened. I don't want to do it without my friend. Okay. So, you all know what you're doing? Right, so boys over here. Girls over here? Well, I'll get out of the way. Are you ready? Okay, react. Oh, a bit more enthusiasm would be nice. Oh, we do. I can see unreacted here. You're not going to get far in life. Okay. Oh, there we go. I'll go and hold hands. It's not that difficult. You'd think I was taking blood, wouldn't you? Okay. So what we've done now, believe it or not, the conceptually easiest. Actually, it's going to turn out to be closer to the demonstration than you'd think. Reaction that you could do, which we've done a simple addition reaction. We've taken 6 boys and reacted them with 6 girls to make 6 boy-girl couples. Okay. So if you go and sit down in the front 2 rows, we're going to use you again in a minute. So that was an addition reaction. And so in here, we should have some hydrogen and oxygen. Hydrogen reacts with oxygen really, really exothermically. So what's going to happen when I take the lid off of this? Nothing. So that's a bit of a problem, isn't it? You know, hydrogen and oxygen react really, really strongly. But nothing happened there. So we need to think about other ways of doing reactions. So can I have you back? Right, and I now need, because we're on 6, I need 6 more girls. 1, 2, 3, go on, 4, 5, 6. Here we go. So you can do something slightly different this time. So if you go and join the other girls. Right, and you've got them lot. So, the problem that we had was that although our hydrogen can act with our oxygen, it didn't. And we need to think about things that we do as chemists in order to make things react. And one of the things that we do, and this is very, very, very common, is we make something first that's going to be more reactive than our original starting materials. And then we do a different kind of reaction. So you know what you're doing? Yeah, over this way then. Right, are you all ready? So what we're going to do now is a substitution reaction. So off you go, react. Start reacting. Keep going. Oh dear. Oh dear. Oh, have you been left on your own? If you've been left on your own, come with me. If you've been left on your own, come over here. Oh dear. So, what we've done now is we've got an unreacted starting material. So if you come over with me as well. We've got our products. We have managed to make the product that we wanted. We've managed to make our boy-girl combination. So thank you very much. If you'd like to grab a seat. Not you lot. But what else have we got? We've got our unreacted starting material. Well, we'll deal with that in a minute as well. That's a bad thing. Not managing to react everything that you wanted creates, I'm sorry about this, some waste. Unreacted starting material waste. Can you go and sit down? Not you four? Because you're a different kind of waste, aren't you? So you are the byproducts of the reaction. And so every time we've made a molecule of the stuff that we've wanted, we've made a molecule of something that we didn't want. And they are, I'm afraid, waste. So, we can make things more reactive, but when we make them more reactive, very often that leads to, well, one, we have to make them in the first place, so we've done another process which has used more energy, more stuff, but also we generate waste. Now, fortunately, there are some technologies that can help us with this. And the technology that we're going to look at now is called catalysis. Has anybody heard of a catalyst yet? Oh, right, okay. So you know what catalysts do. They make reactions go faster. Okay? And so what we're going to do now is set up an experiment where we're mixing some soapy water so you can see what's going on. Some hydrogen peroxide. Does anybody know why we use hydrogen peroxide lots? Yeah, hair dye. And we've got a catalyst in there to make it react. So as you can see, there's nothing happening now. You ready to go? So what's reacting here is, I think it's starting to come. So what the catalyst is doing, it's helping the hydrogen peroxide produce the oxygen. It's the oxygen that does the bleaching. Is it coming? Ooh. Just encourage it along. And there we go. Clearly not the rate at which you'd want it to be operating on your hair. And so we can see a catalytic reaction there. But that's not really very dramatic, is it? Are you ready? So, okay. There we are. Right. So now we're going to show you another catalytic reaction. Oh, no, this one's not. Got your earplugs? So, remember I said hydrogen and oxygen, they react extremely energetically. But we couldn't get them to react. One of the ways that we can get them to react is to set light to the hydrogen, to put a flame to it. But another way we can get them to react, are we ready? Is to add a catalyst. And that's what a catalyst does. It makes the reaction go faster. So, I now need my 5 boys and 5 girls back. So, 1, 2, 3, yeah, come on, 4. 1. Oh, let her out if she wants to go. 1, 2, 3, 4, 5. And so now we're going to show you how a catalyst works. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so my 2 catalysts are just taking their earplugs out. Actually, no, leave them in. Taking their gloves off, absolutely. And they are now going to catalyze the reaction. So remember, we had this addition reaction, which didn't want to react. And so we've added a catalyst. So what the catalyst does, are you being the catalyst, Mel? The catalyst reacts with one of the reagents, and makes it into a more reactive state, and then passes it on to make the product. But you'll notice this time, my catalysts haven't been destroyed. My catalysts can go on again and again and again until the reaction is completed. No byproduct. No unreacted starting material. And catalysts that I can use again. Okay, so thank you very much. So really, that's all we wanted to tell you about today. There's plenty of room. Okay, so the products of the chemical industry are really, really, really important. Not wasting them is really, really, really important. And finding ways to make them where we don't make waste is a way in which we will be able to go into the future without needing holes in the ground that we don't have, without polluting the planet with waste materials that we can't destroy. And that is how we're going to make a cleaner world with chemistry. So it just remains to me to say thank you for listening, to say thank you to Mel and to Laura for demonstrating the experiments today. Thank you. And I suppose to say, do you want another bang?
Yes.
Go on then. Oh, you'll be able to see the point where you need to stick your fingers in your ear. Oh, they've lost their spatula. So for those of you that have done a bit more of this, I can tell you that the catalyst they're using is platinum metal. And typically, like many of the transition metals, it's regularly used to catalyze industrial reactions. Merry Christmas.